Welcome to lesson 6, where we're going to keep on looking at data types. The previous lesson we started looking at data types, and we also looked at identifiers, what are legal identifiers, and so on. In this lesson we'll be looking at the numeric data types, the primitive Java data types. So let's get to it. Now, you've seen this before, so I'm just going to go through it again. Java, you got different primitive types. You got the Boolean, then you got, which can be classified under Boolean and numeric types. Now, we're going to look at the numeric type, and the numeric type is further divided into the integer and the floating point. Now, in the integer, you got the byte, the short, the int, the long, and the character. Okay. Now, the byte is named after the same physical description of how many bits are there in a byte, and there are 8 bits in one byte. So this byte can contain a numeric value of 8 bits. And remember that computers represent numbers or anything in zeros and ones. Okay, why does that happen? Okay, let's just look at it. Counting, we count using the decimal system, and that was possibly because we got 10 fingers and we started counting with our fingers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that is the most likely where the decimal system came from, and we're counting in tens. We bundle then the first 10, and then the next we go 11, 12, and so on. So we go 10 units, 1 to 9, and then 10, and then hundreds, and then thousands, and so on. And yeah, I've got an example of this. Okay, now computers basically have only two states. It's either on or off. And this is closely related to how computers are made, and they're made basically from electronic parts. And it's using, in electronics, either you got a voltage or you don't have a voltage. So a 5 volt or 0 volt. So think of it like this, or a minus 5 volt in most places and in most cases, and a 0. So think of it as a minus 5 volt as a 1, and a 0 as a off state, no voltage. So each little bit is a 1 or 0, means it's on or off in that circuitry, and that's how it represents numbers and characters, anything like that. So it uses, if we're talking about 8 bits, there are possible 8 bits that can be either switched on or off, and a combination of all of them. Okay, so that is how your computer stores numbers and processes numbers and so on, either ones and zeros, on or off, in the electronic sense. Okay, this is known as, where our decimal system is known to the power of 10, obviously we only got 2 states, so it will be to the power of 2. Now, yeah, in 2.1, I'm showing you an example, because we only got, let's take a 4-bit system, we only got a possibility of 4 bits can be switched on or off. So if we want to represent a number, the first bit, the most least significant, if you put it on or off, where in decimal you could have 1, 2, 3, 4, 5, 6, 7, 8, 9, you can either have a 1 or a 0. So the first bit represents a 1 or a 0. If it is 0 there, it means it's off, it would be 0. If it's on, it represents 1. Now, because we got 4 bits here, the next bit we count, it's in the power of 2, so the next one is 2. So if that one is on, it represents 2. If it's off, it represents 0. So if that one is on and this one is on, and then it's 2 and 1, that would be 3. Now in this case, it's the powers of where you'd see it's ones, tens, hundreds, thousands. Yeah, it would be ones, twos, fours, eights, 16s, 32, 64, and so on. But we're looking at only 4 bits here. So when I've got these 3 on, that's 4. That one represents 4. That 1 represents 2, and that 1 represents 1. So that will give you a value of 7. Okay, because that one was off. Okay, so yeah, I've got another example of the maximum number that you can have, where if they're all off, a 4-bit number, it would be 0 because they're all off, and if they're all on, it will be 15 because it's 8 plus 4 is 12 plus 2 is 14 plus 1 is 15. So with a 4-bit number, the maximum I can represent is 15. Okay, 0 to 15. And then the maximum, but that is without being assigned. It's unassigned. It means I don't have negative numbers. What happens if I've got negative numbers? Well, if I got negative numbers, then usually your most significant digit will indicate a positive or negative. So if it's on off state, there is no voltage there. In other words, if it's an off state, it will be a positive number, and if it's an on state, it would be a negative number, or vice versa, depending on electronics work there. Okay, so in this case, because you're giving up these two here, you can only represent with a 4-bit numbering system. You can only represent a maximum of 7 and a minimum of -7, because your most significant digit is now to indicate a positive or negative. Now let's look at the byte. Now a byte consists of 8 bits. That means that a byte can have 8 states. So each bit can be in an on or off. So if you look at it, it's to the power of 2. Your most significant digit will be 128, because there's 2, 1, 2, 4, 8, 16, 32, 64, 128. So on an unassigned numerical value or representative in an unassigned binary, you'd have a maximum value of 255. So if you had to add all those together, depending on their state, obviously let's say the 2 was on an off state, then it would be 255 minus 2, because that one would be off. But your maximum value would be 255, and your minimum value with it all set to 0 would be 0. So this range would be 0 to 255. Okay, but as soon as you need to represent positive and negative values, then your most significant digit will be used for a positive or negative, a 0 being positive, a 1 being negative. So your number range would be minus 127 to 127. Okay. Now, in Java and a lot of programming languages, they use 2's complement to represent negative numbers, not positive. 2's complement to represent negative numbers. So what happens is this here would represent a minus 127, where it is 1, 2, 3, 4, 5, 6, 7, and then your last one your most significant one here would be a 1, which would then represent 127. But in 2's complement, all those are flipped, so they all become 0, and then 1 is added to it. So this would be now represent a minus 127. Would look like this in actual fact, that then obviously the indication of the positive negative. So in the 2's complement, 0, 0, 0, 0, 0, 0, 1, with a 1 there would represent minus 127, because it applies 2's complement. In this case, you got where they're all zeros with a negative, with a 1, in other words, 1 with a whole lot of zeros would be minus 128. And as all zeros, including your indicator of positive, negative, will be a 0, will equal to 0. Okay, and then here's an example of 125. 125, you'll see, is 127 minus 2, because this 2 is not active, so that's 125. Then you flip them all, so all the ones become 0, and the 1, all the ones become 0, and the 0 becomes 1, and then you add it, a 1 to it, so it becomes 1, 1, 1 and a 1 is 1, carry the 1, becomes a 1 and 1 comes 1, and so on. So it becomes 1, 1. Okay. Now, this is what I'm showing here. The byte data type is a 8-bit signed Java primitive integer data type. Its range is from minus 128 to 127. Which you can also remember, if you remember the logic of it, you can remember that it is 2 to the power of 7 minus 2 to the power of 7, because your most significant bit is your positive and negative. So it's minus 2 to the power of 7 to 2 to the power of 7 minus 1. Okay, so let's start working with bytes to see how it works. Yeah, I've got an example, and I'm just going to copy and paste it quickly. Okay, so what's happening here is I'm declaring the variable b1 as a byte, and I'm assigning it a value of minus 128. Then b2, also of type byte, I'm assigning it a value of 127, and then I am printing out the value there. So let's just save this, and I'm going to compile it quickly. So I'm going to say javac, and I'm going to say lesson 6 main.java, and let's compile them. If I run it, java lesson 6.main, and you'll see I printed out b1 is equal to 128 and b2 is 127. Now what is important, I just want you guys to take note of, is that this value here, minus 128, is known as an integer literal. And note, I'm not saying byte literal, I'm saying integer literal. And this will become clearer later on. And this one as well, literal. Okay, so these two are known, these values here are known as integer literals. Now let's say I change this value to minus 129. And let's make this one 128. And let's save it. And I'm going to compile it. So let's compile it quickly. It's javac lesson 6 main.java, and it's giving me two errors. You see there, two errors. It's telling me, yeah, at integer literal, it's got a problem with a value of minus 129, and at b2 it's got a problem with 128, and I'm sure you guys have picked up why. Why is this? If you recall, I went and explained to you guys how Java uses and our computer uses binary number. Remember, we're using a byte here, and a byte can hold how many values, and this is assigned. So a byte is a signed value that can hold minus 128. Its range is minus 128 to 127. That is legal literals, integer literals that Java allows in a byte, because it knows the byte can only hold values from there to there in that range. And as you can see, the smallest number a byte can hold is minus 128, and we've gone and made it 129, so it can't hold it. And 127 is your maximum number in that range, and we went one above it. So now we're getting that error, as you can see over here. Now, another thing I want to bring your attention to is, if you look at the message on top here, stands incompatible types, possible lossy conversion from an int to a byte. Now, recall what I told you earlier. This here is an integer literal. So this value minus 129 is not a byte, it's an integer literal. It's an integer. And this one here as well, it's an integer. Now integer, if you look over here, it's a literal of type integer. Now if you go look here, it is an integer. Okay. Now a byte is 8 bits. A short, which we'll come to soon enough, is 16 bits. And an integer is 32 bits. So in actual fact, this is a type of a type integer literal. Now in Java, it knows that from the range of minus 128, the integer is in the range of minus 128 to a range of 127, fit inside a byte, is allowed in a byte. So it allows you to assign a value of, say, minus 128 and minus 127, because it's in the range. But as soon as these integers are out of that range, it's going to complain, and it's going to give you a compile error, tells you that it's incompatible. Suddenly it's saying that an integer doesn't fit in a byte, but if you had a 1 or a 125 or something, it would fit. And another thing it's telling you here is there's a possible loss of conversion. Now, if you're really sure and you do want to say, I know this is minus 129, it doesn't fit, but I want to force it to fit. This is called casting. So what I could do here is I could cast this value to a byte. I could cast it to a byte. I put the byte inside brackets, and what I'm saying is take this integer literal and cast it, make it a byte value. Okay, and the same thing is happening here. So I could also cast this one to a byte, but what will be the value at the end? What will be printed out here? So let's look at that. I'm going to save it, and we're going to run it quickly. So I need to compile it. And now, you see now, because I've got the cast in there, it is not complaining anymore. Because I'm telling it, I know there's a loss of conversion, but I want this value in a byte. Okay, so let's have a look what happens now. If I run a Java, now let's look here. This value there is, I'm assigning minus 129 to be 1. I'm casting it to a byte, but it's telling me that the value is a positive 127 now. And when I take the positive value, it now says it's a minus 128. So what's happened over here? Let's just show you something quickly. And what I'm going to do is, you'll see the range here. So my range is minus 128 to 127. That's a byte. And these, I'm just showing different numbers. So it goes minus 128, minus 127, minus 126. So from smallest to biggest. And the same thing here. Now, what they're saying here is there's a possible loss of due to conversion. Now, what's happening? It's overflowing. So if you look at this, minus 129 is how many bigger than the least I can have. Minus would be 1 bigger. So it overflows and it goes to the beginning. So that becomes 127. So it overflows by 1. Now, minus the plus 128, it's now overflowed in the opposite direction by 1. So it becomes minus 128. You see there. So if I had to say, yeah, let's overflow this one by another one, and let's overflow this one by, say, another 4, and we save it. I'm sorry, I want to add here. So this one will give me minus 129 minus 1 will give me a minus 130 integer value. An integer value of minus 130. And this one will give me an integer value of, well, 128 plus 4, which will give you 132. Eh? So if I go and save it now, and I compile it quickly, it's fine, and you know why it's fine, because I'm casting the result. And look what's happened now. Let's take the first one. The first one is minus 130. Now the maximum I could have is 128. So 130, 128 is 2 times bigger. So it overflowed by 2. 1, 2. So that's its value it's going to give you. So it goes all the way back like this. And then 128 plus 4 is it's 5 times bigger. Eh? Yeah, 5 times. So because 128, 127 to 132 is 5. So it overflows 1, 2, 3, 4, 5. And the answer should be minus 124. And there it is. Now, all of the Java's primitive types have a corresponding class type or object type of type class. And you have added them here, and you'll see that a class differ basically with a capital, and that's one of the syntaxes. When you see a capital, it usually denotes a class. Now, the byte, its corresponding class is byte. The short, int, notice it's integer, long, float, and obviously this one double. The small and its class is double. Now, you can use objects. The classes have got methods and other properties and so on, which we'll get to later. But what I want to show you here is I can get the maximum and minimum values allowed in a byte by just using its corresponding class, which has got a static value, a constant, which will give me its minimum value and maximum value. So if I save that, which is, if you look over here before I save it, which I'm using that class byte, corresponds to the byte there, the class byte dot min value, and this is known as a constant, a static value, which it's holding a certain value. Okay, so if I save that and I go and compile it, there it compiled, and now if I run it, Java lesson 6.main, and you'll see it printed bytes min value is minus 128 and its maximum value of the byte is 127. Now we need to pay special attention to this literal, integer literals here. They are constants. What I mean here, their values are known at compile time. Okay, so they are fixed. Once these literals are assigned to the byte value, they cannot change. Another thing we could do here, you can also use brackets to understand this better. So you could say that the casting over here is on all this, on this whole number like that, and the same with this one, because we want this whole, but because it's known, it's legal the other way as well. So if I go and save this and I compile it, let me just clear this screen. Okay, I'm going to say Java lesson 6 main.java, and I compile it. You see it compiles, and if I run it, Java lesson 6 dot main, you'll see it's working fine. I've got the 126 there because it overflowed, and I've got the minus 124 here because of the overflow. Everything's working the same. Okay, but what's important here to note, at runtime these values are known because it's a literal. Now I want to show you another example quickly, what I mean by they're known at compile time. Okay, so yeah, I've got another example of a code, and similar to the ones on the top, but what I'm doing here is, yeah, this is a literal. I'm assigning B3 to 12, which is legal, it's within the range, and B4, which is 10, which is within the range. So I don't need to cast this. But yeah, I'm assigning the result of B3 over here to a string literal. So I'm not assigning a literal here like a literal. I'm assigning the reference to 12. So this is a reference to the value 12. See this as this thing here is a reference to a value in memory with the value, and in memory this has got the value of 12. Okay, and here I've got B4, which is a reference to a value which I've assigned a literal, the same as that one, of I believe it's 10 over there. Okay, so but here I'm assigning this reference over here. So what I'm doing here, if I had to draw this B3, this reference, I'm saying result 1 is B3, this one here, plus a literal of 2. And yeah, I'm going even further. I'm saying result is B3 plus B4. Now, these values are not, I'm not assigning a literal anymore here. I'm assigning a reference which is got a value. Okay, what will happen in this case? Let's go and see what will happen in this case. If I go and compile it, and you see it's giving me the same problem, incompatibility problem, because it doesn't know, even though this value and this value is legal, it doesn't know at compile time. It knows this is at compile time is legal, but at runtime, because I'm applying a reference here value and not a literal, this value could change. I could then say something like, programmatically I could call a method which would say B3 is equal to 1025, and this is totally legal. So it doesn't know what this value is here. Okay, so that's why it gives me the same errors now again, because this is not a string literal. This is a reference variable, and this reference variable points to a place in memory that holds the value, be it a literal or not, and this variable could change. Okay, and that's why it won't compile. So it will force you to cast it. So and I could cast it to a byte this way, but I'd have to cast the whole result like this, and this one I would also cast it to a byte, the whole shebang there as well. And let's try and compile that. And there it works. If I run that Java lesson 6.main, and you'll see the result for one is 14 for that one, which is 12 plus 2 is 14, and the second one I've got 12 plus 4. The references are pointing to those literals there, and that will give me 22. Okay, now why this is important, what I'm trying to say here is your integer literals are known at compile time. They are constants, which your references are not or initialized at compile time, but because they are references, they can change value, and that makes these two illegal, because the 12 could become something that's not in the same range. But now to show you my point, I can, if I make these final, there's a special word called final, which means once you've set it, you can't set it again. So if I make these two final, now I don't need to cast it anymore. So I can say B3 plus like that, and I could also do that and say that, and the final keyword tells me that I've set that reference to B12, to this integer literal B12, and because I marked it final, it won't change. I'm telling compiler, that's it, I've initialized it to that value. Let's see what happens now. If I save it and I compile it now, and I compile it, and it's happy, you see. So if I run it, there it's running fine, as you can see. So let's see, let's try and change, just to prove the point here, let's try and change B3 to another value. I'm going to say B3 is equal to, say, 25, which is still a valid inside there, but now I've changed B3. I've told it it's final here, and here I'm trying to change it. And if I save it, compile it, Java lesson 6 main.java, and you see it's giving me error. You cannot assign a value to a final variable B3. So what I'm trying to show here is integer literal is final at compile time. It is known at compile time. It cannot change, just like a reference variable that you've marked final. So it will know at compile time if these are for final values, if they are valid or not. Otherwise you need casting, and a final, we introduced a final keyword, means that if you want to initialize a reference variable to a value, then and you want to make it if you make it final, that reference variable won't change. To emphasize this point, to make sure you can see it compiles here. So 12, and if I go and compile it, you'll see it compiles there. Just let me clear this again so there's not, and if I say javec lesson 6 main.java, it knows that because it's final and this string reference here, integer reference, sorry, is 12 and that one is 10, they're both legal, and because this reference can't change, this is legal and that is legal because it's still within the minus 128 to positive 127 of the byte. Okay, just to show this, if I change this one, say I make this one 1200 and I save it, let's see what happens now. Because it's final, it knows this is its final value, cannot change at compile time. So what would its result be? And again, you'll get all these errors because it will tell you incompatible type, you'd have to cast and things, and then you'll lose due to conversion overflows. So here you see it's giving me an error on this one, and because I'm using B3 here, it also knows it, even though it's final, this B3 is too big and this B3 over here is too big, so it just doesn't compile. Okay guys, let's recap on what we've done today. Okay, we looked at the byte data type, and we saw that it's a 8-bit signed Java primitive integer data type. We saw that it can store values between 128 and negative 128 and positive 127. And this is the smallest integer data type that's available or you can store in Java. Okay, so byte variables are used when a program uses a large number of variables whose values fall between the range of minus 128 to 127, or when dealing with binary data in a file or over network. So files are written or the values are written to a file as bytes or over a network as bytes. Unlike int and long literal, there is no byte literal. However, as you guys saw before, we can make use of integer literal to assign values to the byte variable. Okay, we come to the end of this lesson 6, where we covered bytes. I hope you guys enjoyed it. Don't forget to subscribe to my channel by clicking the subscribe button, and if you want also the notify button, and take note that this is a channel, and hope to see you in the next lesson.